This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill in for Catherine Jen. Connecticut has many alter egos, the land of steady habits, the Constitution State, and the Nutmeg State. Now we may need to add another, the Quantum Corridor. With a $1 million grant in hand, UConn and Yale are leading initiatives to develop quantum technologies and workforce opportunities in our state. Today on Where We Live, we break down these projects and learn about the future of quantum. And yes, we'll try our best to explain what exactly is quantum mechanics, but we only have an hour, so we'll try our best. Joining us now is Michael D. Donato, the UConn Tech Park Business Development Manager and Quantum CT UConn Project Manager, along with Stephen Gervin, the Eugene Higgins Professor of Physics at Yale. Mike and Stephen, welcome to Where We Live.
Thanks so much for having us.
Yeah, it's a pleasure. Thanks for coming in on this snowy morning here. So, Steve, I guess we'll start with the basics. We'll just dive right in here. What is quantum mechanics?
Well, as you said, it's not so easy to explain, but I'll try to give the listeners a sense. So let's start with classical mechanics. That's the 300-year-old theory that explains the trajectory of baseballs and satellites and rocket ships, and invented by Isaac Newton and Galileo. And it works extremely well and lets us land people on the moon with great precision and so forth. But it turns out that it fails when you get down into the realm of the extremely tiny, when you're talking about individual electrons or individual atoms. And there, quantum mechanics is the description of what happens. And it's a strange microscopic world in which particles can act like waves and waves can act like particles. So in the sense that a particle can act like a wave, in the sense that a wave is kind of has its energy spread out over a big area, like a water wave. And whereas a particle you tend to think of as being in a single spot at any moment. So there are many non-intuitive features of the quantum theory, but it turns out to be the single most precise and best tested theory in all of physical science.
And this was a theory that, puzzled some of the greatest minds. I mean, Einstein, I think, was kind of scratching his head at some of the weirdness that came kind of in hand with this theory, correct?
Absolutely. I mean, ironically, Einstein made many of the foundational contributions to quantum mechanics, but he was very concerned about one particular aspect of it, which is randomness, that even when you do exactly the same experiment over and over, you can get different random results. And he liked to say that God doesn't play dice. But in fact, he understood quantum theory so well that he put his finger right on the most strange paradox associated with these random results. And the big irony is that today, when we're building quantum computers, we do the thing that Einstein said should be impossible as an engineering test to make sure that our computer is a quantum computer and not a classical computer. So the thing that Einstein worried about most is now a thing that we're trying to use to build new technologies.
And Mike, we're going to talk a lot about that technology here as the hour progresses. But I wonder if you can maybe just step back a little bit, Mike, and talk about sort of the history of quantum mechanics and where this all got started.
Well, perhaps what I can do, Steve, Dr. Gervin probably understands the history a little bit better than I. But what I can communicate is, for Connecticut and what we're trying to do here, quantum is a a really good choice for a technology to pursue. We in Connecticut have a really strong foundation to support quantum technologies. We have, this beautiful union between our state's Research One universities with UConn and Yale working together on Quantum Connecticut. We have existing major economic clusters in the state in industry that is interested in quantum efforts like defense and insurance and pharma. And really, I think that the time is right as a society, we are at the cusp of quantum significance. So it's the right time for us to step up and invest in the effort to set up Connecticut as an academic and economic powerhouse in the global quantum economy. But I'll pass it to Dr. Gervin regarding the history of quantum and how we ended up where we are.
Sure. So we're actually approaching the 100th anniversary of the development of quantum mechanics, and it was developed by people just doing really fundamental research, asking about the color of light that's emitted by atoms, like the color of a neon sign is different than the color of the sun and so forth. And they were asking questions about the nature of reality and very fundamental things that would seem to have absolutely no applications. And yet it was the quantum theory that produced the tech revolution of the 20th century. With the quantum theory, people were able to invent practical devices, the transistor, the laser, and the atomic clock. And these were the basis of really the massive technological revolution that led to high performance computing, cell phones, lasers, power the communication through optical fibers on the internet. And the atomic clock is the basis of the global positioning system. Just to give you a scale of the impact of this first quantum revolution, today, in every second of every day of the year, the world produces more than 20 trillion transistors. It's just amazing. But in the last quarter century, people thinking harder about quantum mechanics have come to understand that some of the weirdest features and non-intuitive features of it are actually things that we can take advantage of, that the technologies from the 20th century to build what you might think of as quantum machines did not take full advantage of the power that quantum machines could have. And the new kinds of quantum machines that use these features that Einstein found so difficult to believe could be true include new kinds of computers, quantum computers, that could be, if we can build large ones that work well, it could be extremely powerful for solving certain important computational problems. And quantum sensing, the ability to measure very tiny signals of all kinds, whether that's signals from outer space, from the collision and merger of black holes, or sensing tiny signals for intelligence gathering. There are many, many applications there. And the third area is new quantum materials, devising materials that could be used in possibly new types of chips or sensors or detectors or other applications that we don't know about yet. So we're kind of just in the earliest stages of this second quantum revolution. And we don't know yet, what technologies will really appear out of this, but they at least have the potential, if we're successful, to be as important changes as the tech revolution of the 20th century.
And before we kind of dig in a little bit deeper on some of those potential future implications, Steve, I wonder if we can just back up and maybe talk a little bit more about some of the weird features of quantum mechanics. You had mentioned at the start here particle wave duality. Give us the real basic, and for me, really basic, 101 explanation of kind of what that means, and then maybe speak about some of the potential implications that could have in a field like quantum computing.
Yeah, so it's imagine that you have a particle, and it's not really correct to say that it can be in more than one place at once, but that's kind of the shorthand language that we use in to avoid all the technicalities.
Yep.
And that means that the particle is kind of spread out all over the place like a wave. It might be here, it might be there. Well, why might that be useful? Well, imagine you had a computer which runs on, bits, and the bits can be 0 or 1. They can hold the answer to a yes/no question. And it seems like a bad thing to build a quantum computer where you're uncertain whether the bit is 0 or 1. That doesn't seem good. But from a different point of view, it's both 0 and 1 at the same time. That's not literally correct. It's kind of a shorthand, but it gives the idea of sort of the mystery. And if that's true, then the computer can kind of do more than one thing at once, and can be therefore very powerful for solving certain types of problems. There are other weird things. Quantum entanglement, which is Einstein called spooky action at a distance, and he didn't like it. But it's if you do one thing if you have two objects which are entangled, it means that if you measure one of them or change one of them, the other can, even if it's far away, can change. And this can lead to amazing things such as quantum teleportation. You don't send a physical object from one place to the other, but you can send the quantum state of an object from one place to another in a process which even we professional quantum physicists view as rather magical. And you can use this inside a computer to, in computers, you need to do certain operations. You need to change a 0 to a 1 if another bit is 1, let's say, and to do yes/no logic. And you can do that remotely to a bit on the other side of the computer using this spooky action at a distance.
One other thing, Steve, that I found, frankly, just it kind of made my brain melt a little bit was if you observe something in the quantum realm, that can actually kind of change it, and in some cases actually ruin it for the uses you might be trying to put it to use for in, say, a quantum computer. Can you just, at a very basic level, explain that sort of quantum weirdness?
Sure. So this is actually a very important point, and it's a massive engineering challenge for us. So imagine that you have to observe where a particle is, then you have to shine light on it, to, like with a microscope, to image where it is. And it turns out that since light is not just a wave, but also a particle, the energy in the light wave comes in little lumps called photons. When they hit the object that you're trying to measure, they give it a kick when they bounce off it to form the image. And so that if you learn where the particle is, you now no longer know how fast it's going because you're not sure how hard it got hit. So that's the Heisenberg uncertainty principle. And in quantum technologies, let's say a quantum computer, you would like to have a quantum system execute a program, and it turns out that you can't observe what's going on in the middle of the program. You have to wait until the end to get the result. But unfortunately, it's not just you that's wants to observe, but the whole environment around the computer is capable of detecting or observing what's going on. And so we have a huge engineering challenge to kind of isolate the quantum bits or qubits in a computer from the environment. So they're kind of operating in the dark. We don't know what's happening, and their wave-like properties can kind of propagate around inside the computer without being disturbed by any observation. And that's very difficult to achieve. We have to, in our particular technology with superconducting circuits, we have to cool them down in a refrigerator to very close to absolute zero and take other extreme measures to prevent the environment from observing what's going on. But then at the end, you want to know what the answer is from the computer. So you have to strongly observe and measure what's going on. And turning that observation on and off very perfectly is one of the big engineering challenges.
Mike, I wonder if you can talk a bit about the challenges of just getting people to understand quantum mechanics here. As you know, we're looking to build up a workforce of people, students who are interested in pursuing this field. From what Stephen is saying, it sounds like it's a challenge for people who have a really, really good grasp of science. So what are the challenges that are just out there for getting to people to understand this really kind of weird field?
You said it, Patrick. It's very non-intuitive for anyone who's kind of we'll say anyone who's an adult, because it's just so counter to what you're used to. And as we try to advance quantum technologies in the state, kind of quantum literacy is something that we have to consider really carefully. How do we educate? How do we share knowledge on this deeply mysterious and complicated topic? Curiously, I said adults. I think kids might actually have an easier time grasping some of this stuff because they're not tainted by preconceived expectations. So you can tell them about a particle being in multiple places at once, and they don't necessarily discount that as an impossibility. They accept it and move on. Education is a huge piece of this, and we have to approach it at all levels. So, as we look at quantum technologies and adopting it within the state, it's not just high academic. It's not just the PhDs. We want to drive this initiative through everyone and get to the point where we can start bringing quantum to students so that as they age and become educated and enter into the workforce, they'll be ready to accept this very different world that we may be facing.
You're listening to Connecticut Public Radio. This is Where We Live. I'm Patrick Scahill. With us this hour to talk about the future of quantum technologies in Connecticut is Mike DiDonato, who you just heard there, the UConn Tech Park Business Development Manager and Quantum CT UConn Project Manager. Also with us is Steve Gervin, the Eugene Higgins Professor of Physics at Yale. Do you have a question about quantum? I know I have many. I'm trying to get them answered today. 888-720-9677. That's 888-720-WNPR. Or you can find us online at Facebook and Twitter at Where We Live. We'll be back after this break. This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill in for Catherine Shen. In May 2023, the U.S. National Science Foundation awarded a $1 million grant to Yale University and UConn toward developing quantum technology-related businesses in Connecticut. That's according to the Quantum Institute at Yale. Back with us on the program today are two people leading this effort, Michael D. Donato, the UConn Tech Park Business Development Manager and Quantum CT UConn Project Manager, along with Stephen Gervin, the Eugene Higgins Professor of Physics at Yale. So, Michael, I'll throw it back over to you. Quantum has been a part of Connecticut research for a while. Can you just talk a bit about the grant that was received here to really kind of jumpstart this industry here in Connecticut?
Gladly. So, as you mentioned, the National Science Foundation put out this call for regions to build a regional innovation engine, which is essentially a network of connection or a connection of various institutions that all work together to push forward a technology. And think kind of Silicon Valley, except instead of a focus on microprocessors where we want to pursue quantum technologies. And there are 44 different regions that are pursuing this grant and all focusing on different areas. So some focusing on healthcare, others on advanced manufacturing or artificial intelligence. And we chose quantum because it seems to make sense for the state.
So I did want to actually jump in to ask about the healthcare aspect here. So we spoke a bit in the prior segment about quantum computing and just kind of the basics of how it works. I guess when we think, Mike, specifically about the healthcare sector, what are some implications there for how this technology could yield benefits there for people?
You know, it's interesting. Quantum technologies have potential to have a really broad impact. And as Steve mentioned, we don't know exactly where it's going to go, but we do understand the potential. So for the healthcare industry, we might be talking about major advances in medical imaging, certainly strengthening of security, which is so important with all of people's health information being stored electronically. The speed and capabilities of modeling for computers is expected to is certainly on the table. So when you think about the healthcare industry, imagine a future where it's easier to diagnose issues, it's easier to design pharmaceuticals to help treat interesting medical conditions, and able to, do all this more precisely and more accurately than we could currently imagine.
Steve, speak a bit about modeling speed on computers and how, a quantum computer, we sort of touched on this last segment, but particularly when it comes to maybe healthcare implications, how it could possibly yield faster results there.
Yeah, so the thing to understand about quantum computers is, they can be faster at solving some problems or even solve problems that essentially would be impossible on any imaginable future ordinary computer. And it's not because their clock speed is faster, because they're doing, more operations per second. They're actually probably slower. But algorithms that you can write on a quantum computer allow you to do things that just can't be done with a traditional computer. So I mentioned, so certain problems, let's say solving the equations that describe, and they're actually quantum equations, that describe how a drug molecule binds to a target. You want the drug molecule to go and stick itself into a little pocket on a certain other molecule in order to for the drug to be effective at whatever it's supposed to be doing. And those equations are very, very hard to solve, but they're very natural for a quantum computer, since it runs on the equations of the quantum theory. It can solve those in a sense. That's one example. So you could sort of virtually design different drugs and predict before you try to make them in the lab, will they bind to their target? Will they do what they're supposed to do? That's one example. Other examples, Mike mentioned security. So this thing we were talking about earlier, that the observer can change a quantum state or ruin it. You can use that to encrypt information when you're transmitting it, let's say, over an optical fiber. So in that someone attempting to eavesdrop and steal the information will change it, and actually that can be detected, and it turns out that it can lead to an increase in privacy. That's another example. Then, under quantum sensing, just making measurements in the medical domain is very interesting. People are doing, for example, imaging of the connections of different neurons in your brain using special light sources that improve the quality of the imaging, and it's based in part on quantum principles. You can today build a quantum thermometer that's really tiny, microscopic piece of diamond, actually, and you can insert that into a single living cell and measure the temperature. And if the cell is active, its metabolism is going strong and it's doing some task, the temperature will be slightly higher inside that cell, and you can actually measure that. So that's an example of quantum sensing. But we don't really know where this is all going. It's very, very early days. There's a lot of hype, so I don't want to oversell, what's possible. But the potential for many different advances looks very exciting.
Mike, how is the country, just the U.S. government, thinking about this? I mean, Steve mentioned some possibilities for encryption, for example. I understand the grant that was given to UConn and Yale as part of a broader national initiative. Maybe just speak a little bit more about the National Quantum Initiative that's going on here in the U.S. currently.
Sure. For the specific NSF grant, they're looking to address critical national and societal challenges with these the building of these regional ecosystems. And you listen to the examples that Steve gave, and they're really exciting. And you can see the possibilities here. So it's unsurprising that quantum technologies would be seen as a critical national challenge. The value to the defense industry, again, an industry that's so prevalent in Connecticut, is vast. But not just there, but also all of the supporting industries like material science, the potential to design and develop new materials could be critically interesting and necessary for the United States of America. Globally, there's a race going on to develop quantum technologies as quickly as possible because it will give us an edge. Um, and we're we started a little bit late to the game, the United States, but we are moving extraordinarily fast. The amount of industry investment into quantum research um, is staggering. And I think that the reason is obvious as you think about those examples from, what will taking the temperature of a cell allow us to do for the body? What will the development of new materials do for our defense industry? How will the more effective security and being able to ensure that our data is private affect the United States' role internationally? All of these are critical questions that quantum will play a part in.
How do you see the workforce developing for this, Mike? And why is it important to, educate future scientists about quantum mechanics and all the implications that it could have?
We talked earlier about the challenge of educating on such a counterintuitive topic. And we've talked about the importance of quantum technologies, the important role that quantum technologies could play in a vast number of industries. Let's look at, just think about, say, manufacturing. Connecticut has over 4,000 manufacturers, an incredible number for a small state. And quantum technologies could impact these companies with improved optimization, sensing and imaging, precision measurement, and data protection, as we've mentioned. But if you think about that for a moment, there's an education gap here that we have to approach very carefully. It's not, I mentioned earlier, this isn't just for PhDs, and it's not, if for any of those 4,000 manufacturers in the state, they need to have some sort of awareness of what's happening with quantum because they may find that they're using it to improve supply chain in the future. And growing that awareness will strengthen our ability to move in that direction and to take advantage of it when it comes. So that's why education is so important. And as we have been building the partners for this effort, this Quantum Connecticut effort to build a regional innovation engine here in the state, we're making partnerships with organizations that will help us on all fronts, and education being one of them. So, for example, we're super excited to have the Connecticut Science Center on our team because we need to be able to present quantum ideas to kids who are, 6 to 12 years old. Let's get them engaged because when they're older, even if they're not going to pursue higher education, even if they're going into technical fields or if they're going to work at one of those manufacturers in the state, having an awareness will be a valuable skill for them to have, quantum awareness.
In the next segment here, we're going to be speaking with a high school educator who's doing just that. Mike, I guess I'll just ask you real quickly, and then Steve, one more question before we break here. But for Mike first, you mentioned attracting people to Connecticut, to work here, to work in this field. Connecticut isn't Silicon Valley, right? We do make a lot of stuff here, but I don't think we're out there as Silicon Valley level. Maybe I'm from Connecticut, so I can be a little self-deprecating. But just talk about the challenges of attracting people to Connecticut versus, say, Silicon Valley or other tech hubs when it comes to working in the field of quantum technologies.
I think this is again, it's not just Silicon Valley for sure. There are tech hubs all across the United States, and the challenges, especially as it relates to workforce and attracting capital and attracting entrepreneurs to the state, those are real challenges. I think that we as a state are in a good space for it. We've seen some optimistic news recently about the number of folks that are moving into the state, the number of graduates who are staying in the state for working after receiving their education. So I think we're doing a good job on that front from a time perspective. And hopefully this Quantum Connecticut effort, can attract more capital and attract more entrepreneurs by creating an environment that is deeply supportive to those people who are looking to advance quantum industry or quantum research. So I'm optimistic on that front.
And Steve, I guess speak a little bit about how you and others just make the case for funding this type of research. We obviously, we talked about lots of the implications that it could have in the future. There's always the balance of future problems versus today problems. So just sort of make the case for why this is technology that's worth exploring and worth funding.
Yeah, so I think that there's worldwide interest in developing this technology. Europe, for example, the European Union is very explicitly doing this because they missed out on the 20th century tech revolution and learning how to manufacture computer chips. And they're so it's a kind of national economic security interest explicitly for them. China's investing heavily, and the United States is as well. And I have to say, the United States government is taking a pretty sensible approach, an all-of-government approach, in which the Office of Science and Technology Policy in the White House is organizing all the different agencies that we make our grant proposals to, from the NSF to the Department of Defense and Department of Energy and so forth. And the pitch that we make first is that this is incredibly exciting, fundamental research, fundamental new science with the potential to produce revolutionary technology. And I want to keep saying potential because we're definitely not at the stage of just reducing this to engineering. But it's very clear that just as the people who invented the transistor would not be able to foresee that 20 trillion per second would now be being manufactured, and that your iPhone would have many billions of transistors in it, we can't foresee exactly where this technology is going, but based on the things that we can see dimly through the fog, there's just tremendous potential for surprising new applications that some we can foresee or think we can, and others I'm sure will come along as surprises. But I want to emphasize that we're still in a stage where we need fundamental research in universities, we need engineering development in companies, and we need communication, like we're doing in the Quantum CT program, between academics like myself and our industrial partners. We're teaching them about what we think quantum can do, and they're teaching us about the real world problems that they need to solve.
Coming up, we're going to learn a little bit more about how students here in Connecticut are learning about quantum mechanics. Because to build a quantum workforce, you're going to need more primary and secondary school students who know about it. So we're going to hear from a high school teacher that teaches quantum mechanics in his classroom. With us today is Mike D. Donato, the UConn Tech Park Business Development Manager and Quantum CT UConn Project Manager. And you just heard Steve Gervin, the Eugene Higgins Professor of Physics at Yale. Both of you, please stay with us. You can join the conversation right now, 888-720-9677. That's 888-720-WNPR. Or find us online at Facebook and Twitter at Where We Live. This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill in for Catherine Shen. Today we're talking about quantum mechanics, and as we heard earlier, quantum theory is something some scientists still don't fully understand. And learning about quantum can start even at the high school level. Joining us now is Dr. Brian Sullivan, high school STEM teacher teaching physics, calculus, and statistics at the Wooster School, a private coeducational school in Danbury, Connecticut. Brian, welcome to our show. Thanks so much for coming on today.
Good morning. Thanks for having me.
So, Brian, speak a little bit about how you've integrated quantum mechanics into your classroom.
So when I've looked at high school physics education, I've observed that a lot of the topics we include both in physics and in math are based on the interests of the space race in the 20th century, but often these other topics, quantum mechanics and other parts of modern physics, have been left out. So I include units in the spring that involve studying thermal physics, and some of that involves Einstein's theory of energy quantization in crystals. And we also study some of the fundamental experiments of quantum mechanics from the early 20th century. So students are measuring Planck's constant by looking at the voltage needed to light LEDs, and also measuring the wavelength of lasers using a CD as a diffraction grating. So some of these experiments can be pretty approachable, but they are certainly not intuitive.
Yeah, well, it's a perfect segue into my next question, which is how do you, for a student who's at the high school level, illustrate something as abstract as particle wave duality with a tangible experiment? So maybe just walk us through in basic terms some ways that you can do that.
So some of what helps us is that we include some Python programming in both the math and physics courses. And that allows students to visualize the wave function, which is one of the main tools of understanding wave-particle dualities. It can be a really complicated entity to understand, but by writing relatively simple programs, we can visualize the time evolution of a system that's described by a wave equation.
How have you seen technology help students grasp these concepts throughout your tenure, Brian? I guess think back to when you were learning some of this stuff, when you were still a student, the tools you had then versus the tools that kids have today.
So two of the things that make some of this more approachable in high school are the prevalence of LEDs in many different colors that didn't exist when I was in high school. Which was the 90s, but also the ease of obtaining lasers of different colors. So we can have single color light sources with very predictable wavelengths, and that enables some of this study. Another thing that really helps is that every student now generally has a device that they can program on, and that certainly wasn't universal 25 years ago.
Yeah, I was programming on my graphing calculator, I think, when I was in high school, and it's not an iPhone. I'll tell you that.
I was writing on my TI-85 as well.
Yeah. How do students react to learning about some of this stuff? I mean, and I guess I asked that from the perspective of, there's the science, right? But there's also, it's almost like bordering on philosophy with some of this stuff. Like where does an electron lie? It's neither here nor there, but it's somewhere within this. It's philosophical in some ways. Just talk about how students absorb this information when it is so weird.
Absolutely. We have a philosophy course here, and I share many students in common with our philosophy teacher. And we enjoy a lot of conversation at the lunch table and in and out of class about the interaction between philosophy and quantum mechanics. We have models that describe reality, but it doesn't mean reality has to adhere to those models. The idea of a wave and the idea of a particle are just ideas that we made up, but it turns out nature sometimes is a little bit trickier than our simple models, even when the models are complex. So this is really a gateway that draws more young minds into physics and math because of how weird it is, I think.
Steve, can I throw that question over to you, just the philosophy of all of this and how it can kind of just expand and kind of hurt people's brains all at once? Just pick that thought up.
Yeah. Children grow up sort of as Aristotelians. They're in a world dominated by friction. They know, like Aristotle, that when you stop pushing on something, it stops moving. And so even ordinary classical mechanics, we don't always have the intuition about frictionless worlds and floating in orbit in space and stuff that we don't have the everyday experience. And it's a struggle to understand. And quantum mechanics, we have even less direct experience with. And what's interesting is that we have a very precise theory, the quantum theory, which, as I mentioned earlier, is easily the most precise and strongly tested theory in all of physical science. We know the recipes for how to predict the outcomes of experiments, how to calculate things that we're going to measure. But the great philosophical arguments begin when we ask, what does it mean, or what does it say about reality? And even professional quantum physicists sometimes get confused or get into arguments, friendly arguments, or philosophical debates about how to interpret sort of the meaning of quantum mechanics. And that's bothered Einstein. It's bothered the inventors of the field. I think young people who grow up with seeing modern, because of the advances in modern technology, they see many more direct experiments that show them that, yes, quantum mechanics has these strange features. And they begin to develop some intuition, but it's not easy.
Brian, I'll throw it back to you here. We only have a couple minutes left, but I guess just speak about going forward, the need for, in your view, more high schools, more physics teachers at the high school level to be teaching this type of stuff as the technology develops, as Stephen is saying.
I think, like I said, we really need diverse thinkers to understand these strange systems. And by not focusing only on the mechanical block and pulley systems that are usually the bread and butter of introductory physics, we can really interest more young people by diversifying what that curriculum looks like.
And Steve, we have about a minute left here, so I apologize for asking a question, but I think you can get to it. I got a 5-year-old son. I mean, I don't know if I can explain quantum mechanics to him in a way that would make any sense, although his brain's pretty plastic, so he might be able to absorb more than I would give him credit for. But how early should kids start thinking about some of this stuff when they're in school?
Well, I can recommend that you buy a copy of Quantum for Babies.
Okay.
There's a serious effort now in education developing sort of pictorial representations of the mathematics in quantum and the phenomena in quantum. And I think we should begin at the earliest ages. Certainly by middle school, you can do some simple experiments. And by high school, I'm very impressed by the kind of stuff that Brian Sullivan is doing at Worcester School. I think it's just really important to, the problem with physics is that 300-year-old physics, unlike 300-year-old biology, is not wrong. Mm-hmm. And we do study pulleys and baseballs and things, but we really need to bring these modern topics in to draw students in. And I think people like Brian are doing an amazing job with that.
Well, thanks to Dr. Brian Sullivan, high school teacher teaching STEM, physics, calculus, statistics at the Worcester School, a private coeducational school in Danbury, Connecticut. Also, thanks to Mike D. Donato, UConn Tech Park Business Development Manager, Quantum CT UConn Project Manager, and Steve Gervin, Eugene Higgins Professor of Physics at Yale. Thanks to you for listening today. I'm Patrick Scahill. Today's show was produced by Tess Terrible.